This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you're enjoying the podcast, and if it's helped you in any way, or entertained you in any way, or you learned anything, please consider rating and reviewing it. Your input is extremely important for helping others discover the show and understand what it's all about. Today, Alberto Salleo will tell us about polymers. Polymers that are made out of organic materials that have uses that will probably surprise you. It's the future of polymers. Before we get started, another reminder to rate and review the show so that others can learn about it and benefit from listening to it. So when we think about polymers, what do we think about? Well, most of the polymers we come across in everyday life are plastics. Plastics are generally inorganic materials, plastic bottles, plastic materials. People are worried about polymers these days because plastics don't break down very well, especially inorganic plastics. And so we now hear about microplastics and we hear about these polymers that are causing trouble. But there are different types of polymers. For example, there are organic polymers. The most famous organic polymers, until the end of this podcast episode, is DNA and proteins. Your genome is made out of DNA, and DNA is a long polymer made out of 4 subunits that are 3 billion long in humans. Protein structures are polymers, proteins that make up your body, make the structure of your muscles, the structure of your eyeballs, the hair, the skin. It's all made out of proteins. It's a polymer. Well, there are also other organic polymers, and they have some amazing properties. They can conduct electricity, so they're useful in electronics. They can be flexible, and so they might be useful for interacting with human tissue for prostheses and other electronic sensors within the body and outside of the body. And they can form the basis for powerful new models for very low energy computing or neuromorphic computers. We'll hear all about this from Professor Alberto Salleo. He's a professor of materials science and engineering at Stanford University and an expert on polymers and especially the possibilities and potential of organic polymers. Alberto, you're an expert in engineering polymers for many uses, and we're going to get into that. But let's start out with a basic definition. What's a polymer?
A polymer is just a very, very long molecule. It's funny that you ask because I actually don't come from the polymer world. My PhD was in a completely different area. And I entered polymers sort of in this unusual application, which is polymers for electronics. Most people think of polymers for bottles or stuff like that. But there was an invention or a discovery, I should say, in the 80s that some polymers can be used for electronics. And I came from that side. And I always joke when I teach a class that it took me 10 years to realize that all the work that I do in polymers can be explained by the fact that polymers are really, really long molecules. But it took me 10 years to get there because I'm not a polymer physicist. And there's a famous book by Stanford polymer scientist, Flory, who won the Nobel Prize, that essentially says that all the properties of polymers can be understood if you realize that polymers are very, very long molecules. So
Now,
that's what a polymer is.
are they always made out of subunits, like repeating subunits, or is that optional?
So they're made of repeating subunits, and then whether they're all the same or you kind of mix things in, that is up to the synthetic chemist, and that can give different properties to the polymer, whether you have 3 units that repeat as ABC, 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 or they're repeated in a disordered way, and there's all sorts of theories for what type of polymer does what, depending on how the subunits are repeated.
Gotcha. And so, as you know, I'm in biomedical field, and in my world, DNA and protein are 2 of our favorite polymers. And DNA, I believe, does qualify as a polymer for sure. And there's 4 building blocks. Proteins have 20 building blocks. For somebody who's not a biologist, who doesn't work on flexible electronics, when do people see polymers in their everyday life?
Well, I mean, like I said, your plastic bottles, your
Plastic
PET
bottles.
bottles, tubing. I mean, polymers really have revolutionized our life. We always think for the better, and now we know about microplastics and trying to have polymers sort of more in a circular economy. So we're being more thoughtful about it, but they're everywhere. And in my group, we're excited about these other applications of polymers that are less obvious. which is in electronics and in bioelectronics. For a number of reasons, they're suitable for those type of applications.
Great, and so let's get into that because it's extremely exciting. When I look at your papers that you and your group have published recently, one of the things that strikes me is you use the word organic polymers a lot, and I don't know if that's 100% of your work or just a big part of it. But what would be special about an organic polymer?
So that's pretty much 100% of our work. For us, organic polymers means that the main element of the polymer is carbon. You could have, silicon-based polymers, but ours are carbon-based polymers. And the reason why it's 100% of our work is because the electronic properties of the polymers that we work with are really given by the carbon atoms and some properties of the bond of the carbon atom. So yeah, our polymers are organic because they're carbon-based.
Does organic imply that they might be more easily biodegradable? You just made a reference to microplastics and some of these issues. Does organic automatically solve that problem, or is it a step, or how does that relate to these issues?
Definitely not automatically, but it does open the door towards that. It opens avenues towards making polymers that can be digested by organisms or could be degraded by enzymes, and there's a big emphasis now in finding enzymes that would degrade these polymers. You have to work a little bit harder at figuring out what backbone structures. If you think of a polymer like a big, I'm Italian, so I'm going to say spaghetto. If you think of a polymer as a big... the backbone is the spaghetto itself, and so you have to be a little bit more thoughtful what you put in there so that something can come in and break it into smaller parts. Ideally, what you'd want is not only break it into smaller parts, but that those parts are the constituents that you could use to remake the new polymer. Then it's really circular, right? Breaking it into small parts is not so useful if then you still have to bury those small parts somewhere. But if those small parts are really the constituents that you started with, then you win, because you make the polymer. Once you don't need it anymore, it breaks back down to its original constituents, and you make a new one with the constituents.
Great. Okay, so we're excited about organic polymers, and you said something very exciting, which I caught, which is that these have interesting electronic properties. And I know that one of the areas you're looking at are like bendable, flexible electronics. So tell me about that. Tell me about where the work is, and are we starting to see it in products, or is it still very much a research phenomenon?
So fundamentally, the reason why you can use these polymers for electronics is, like I said, if you play your cards right with the carbon-carbon bonds, you can have electrons that zip along the chain. Now, you'll never have a device that's made with a single chain of polymer and two electrodes, and the electrons zip from one to the end to the other. You have to make a film. And so where we are now is to connect the properties of the molecule to that of the film, which is what you'll need. And that's really complicated. Think of it if you come from the biomedical engineering side. My understanding is that a sort of a $60 million question or something like that in your field would be, if I give you a molecule, can you predict the crystal structure it will crystallize in?
Yeah.
Because the bonds are pretty weak between molecules. So it's similar here. If I give you a polymer strand, can you predict what structure it will form in a film? And right now we can't. But the properties of the material will depend crucially on that. And that's the bulk of my group, is really that, connecting the structure of the molecule to the structure of the film to the electronic properties. Now, it's interesting because we do this fundamental work, but synthetic chemists are actually very, very good at intuitively making very good materials. And so it's one of the cases where we're lagging behind the creativity of synthetic chemists. They make these beautiful molecules, and they end up working better than expected. By intuition, their intuition works really well. So where we are now actually is the polymers itself. There's this interesting trade-off where if you want to have good electronic properties, you need the polymer to be ordered, sort of crystalline. But then if something is ordered and crystalline, it's brittle, and that's the opposite of flexible. And so there's two areas in my field. One is, can you kind of find that Goldilocks situation where the polymer conducts enough and is flexible enough by itself. And the other area is, let's take advantage of another aspect of polymers, which you can blend polymer A with polymer B, and you get something together that has a little bit of the properties of one, a little bit of the properties of the other. So if you blend a conducting polymer with an elastomer, you have something that could be stretchable and elastic, and at the same time conduct electricity. And that seems to work really well. And in fact, at Stanford, we have one of the world's experts in this area, and that's Jinan Bao. And she's been able to make very, very stretchable, she calls them electronic skins.
Yes.
So that's where we are. The materials, I think, are in a good place. To be realistic, one of the hurdles is if you wanted to make a product, you have to make these things by the ton.
Right.
And no one really knows how to do that in a cost-effective manner. So it's still very much in the research stage. You're not going to see a product very soon. But at some point in our community, we were very excited because Neuralink disclosed, this is Elon Musk's company, disclosed that one of the materials they were considering for their electrodes was one of the polymers that we work with. Eventually, I think they went in a different direction. So it's kind of, getting tangentially there, and the materials are getting the attention they deserve.
Well, let's go right there because you mentioned the Neuralink, and I know in your papers you refer to neuromorphic computing, and it's really exciting. So, how do we get from a polymer to the idea of like brain-like computing? Because there's a couple of steps there, and can you just take us through, because this is one of the most exciting areas that I read about in your work.
Yeah, so I said, okay, these polymers were sort of the electronic properties were discovered maybe in the mid-'80s that they can be semiconductors. So that's just like any other semiconductor. But it turns out that one aspect that's unique to polymers compared to your classic semiconductors like silicon, which is like a rock, is that if you put a polymer in a solvent or an electrolyte, it swells, so it absorbs the solvent in it.
Yep.
So if the solvent has ions, now you start having something that looks a little bit like living matter, right? We have swimming in our brain a lot of ions and fluids. And again, if your polymers are designed properly, these ions permeate the polymer. And you can imagine that if you have an anion, so that's a negatively charged ion, it has to be compensated by a positively charged particle, which could be what we call a hole, so a positively charged particle on the polymer that can conduct electricity. And so it's not hard to see the leap from a purely electronic material to a material where its electronic properties are modulated by ions. And now if you think of a neuron, it's sort of similar, right? You have ion channels that have the ions in and out, and that gives rise to potential changes and so on.
Yeah,
so
in fact, the brain, just to review, neurons are all about ions going in and out of the cell body very quickly, and that's how they propagate these electronic signals throughout the brain. And you're describing something very similar where the positive and the negative charges are slightly separated, and you can control when they get close, when they get far, and their flux, perhaps.
Exactly. With the potential, you push them in and out, and then modulates the electronic properties of the semiconductor. So this gives you two areas of application. One is you now have a natural transducer of ion fluxes into electronic fluxes. And so you can now sense if a neuron is expelling ions or absorbing ions, you can sense that electronically very easily. And then the other area is now using these properties to emulate what neurons do and what synapses do. And so that's what we've been doing. Our emphasis was more on the synapse, so trying to make a device that absorbs ions, and then once it absorbs its ions, it changes its conductance in a way that's non-volatile, just like your synapses are connect neurons, and then you build memories by having those connections be non-volatile or volatile for 5 minutes, or if you have cognitive problems, they become volatile at timescales that are non-desirable.
And when you say volatile, you mean like persistent. A non-volatile would be a persistent memory, or a neuron or a pseudoneuron in a persistent state, whereas volatile would mean it's not reliable and it might change states.
Yeah, just like you would have plasticity, your brain can adapt, and then that adaptation can persist or not.
So when I read about this, one of my big questions was, are we thinking that we're going to and the answer might be both, but I could imagine using this in human brains to help humans who've suffered injury or to increase performance. I could also imagine leaving the human out of the loop and just using these materials to create a new generation of computer. And I'm wondering, is it one or both, and how are those two kind of playing off one another?
It's very definitely both. So in the first one, you're saying have it interface with a human. Another interesting aspect of these materials, and that's one aspect that I've become more and more excited about, is that they're redox active, meaning they can exchange electrons. And so this means that if you have biomolecules that are also redox active, and they all are, you can, for example, neurotransmitters, you can,
Yep.
let's say, oxidize a neurotransmitter, and that will change the electronic state of my device. And so now you have a chemical to electronic interface where the chemical part is a neurotransmitter, which is a molecule you'd have in your brain. So you could imagine a future where the device bridges a gap between two chunks of living matter where there's something missing by interacting with a neurotransmitter on one side and then emitting a neurotransmitter on the other side, for example.
Oh, that really is exciting. So, I mean, I know you're not there yet, but this is basically like an artificial neuron that could be used to replace like a spinal severing of a spinal. And I don't mean to suggest that this is tomorrow, but you've just laid out the vision where you could then use this to basically splice in missing neurons when they've been injured or died for some reason.
Yeah, that's right. I mean, if I were to try to sell, a multi-$100 million program to a program manager, I would say this would be the long-term vision. We're
Yes.
very far from that, but the materials have the potential to do that, and it's really unique. One interesting, cultural quirk of my research area is that it started out with electronic devices, and of course, you can make electronic devices with all sorts of materials: silicon, gallium arsenide, and those are engineered to perfection. And so people wonder, what does your material bring that's new and unique that I can't do with silicon? And often in the world of conventional electronic devices is not much,
Right.
maybe lower cost. But here are properties that are completely unique to these materials. No other electronic material can do something like that. And that to me is exciting because it opens up a completely new area of application that is not accessible with conventional semiconductors.
This is The Future of Everything, and I'm your host, Russ Altman. We'll have more with Alberto Salleo next. Welcome back to The Future of Everything. I'm Russ Altman, and we're speaking with Professor Alberto Salleo from Stanford University. In the last segment, Alberto told us about these new organic polymers and some of their amazing properties. In this segment, he's going to tell us about a new type of computer that may be built out of them, and also new ways to study them with electron microscopy, and some of their applications in batteries. Alberto, we were about to discuss the use of these interesting organic polymers not to interface with human or living systems, but just to interface with themselves to create new kinds of computers. And I wanted to ask you, how would that go? What is the vision there?
Yeah, so there is a lot of emphasis lately on what people call neuromorphic computing, so brain-like computing. The brain is amazing because with very low power, it does very complex things, and I don't know that we really understand why, but people are trying to sort of replicate many of the functionalities of what goes on in the brain. So you can, in three broad categories, you'll have neurons, synapses, and dendrites. And so it turns out the functionality of these three devices can actually be replicated with our polymers. You can make simple circuits. You can make them with silicon as well, but it turns out with polymers, you can make it much more naturally with very few devices. You can make simple circuits that will produce spikes, just like a neuron, and do all sorts of adaptive behavior with small changes to the circuit design. You can make a dendrite where the signal propagates down by having different impulses coming down your polymer film, sort of turning on piece after piece. And if you turn on the wrong piece at the wrong time, the signal gets stopped. So you can replicate what happens in a dendrite. And then synapses, which we've talked about a little bit before. So you could imagine now putting these pieces together and sort of make, I wouldn't call it a mini brain, but the functionality of it. I think if I have to be realistic, the big challenge there is that the connectivity in the brain is just insane. The number of connections that every neuron makes with its neighbors is enormous, and that's very, very hard to replicate. So we can make devices, we can make a plane where they're all connected. Lithography, which is the technique that's used to make computer chips, is very good at that. But it's not very good at doing things in 3D. So maybe that's a big challenge, is how do you connect things in 3D? Because then that gives you the density that you need to maybe start seeing some emergent behavior that could be interesting.
Yeah, I just wanted to just a quick follow up on that because you talked about these films, and I was wondering if the films can be branching or arborized. I mean, that's where the word dendrite comes from. So, I guess in 2D, it sounds like in 2D you have do have a lot of capabilities to do the kind of branching and reconnection, but that when 3D, which obviously the brain and other computers are three-dimensional, that's where the fabrication isn't there yet?
That's right. The fabrication isn't there yet. Some people are having some creative ideas where you actually grow the polymer, right? The polymer, you can polymerize it in situ.
Yes.
So you could grow it and with some electrical potential sort of direct its growth in different directions. And that would naturally, as you say, arborize the structure. I'd say that's more in the realm of science fiction now,
Yeah.
but the idea is interesting.
It's very interesting because my colleagues in bioengineering are doing this with cells, where they're building three-dimensional lattices where they can then get the cells to grow, and they have to make a little bit more progress. But then they might be able to have some principles about how to do like steered generation of materials, because that's what it's all about in a lot of these fields.
Exactly.
All right.
Yeah.
But if those computers can be built, I think we're talking about humongous reductions in power. Is that true?
The devices that we make, it turns out, use very little power to be switched. I don't know if I understand exactly why. One of the reasons is that we talked about how ions go in and out, and the ions that travel in our devices are protons, and those are really light, and they don't consume a lot of energy when they move. And the other reason is, I think the device, a typical electronic device goes from off to on, and there's a huge difference between these two states.
Yeah.
So you have to spend quite a bit of energy to take an electron from off to on. And ours actually operate kind of from a little bit on to a little bit more on, a little bit less on. So they're closer to equilibrium. And you just kind of tweak them slightly away from equilibrium. And that's why I think they use less energy.
Okay, so that's great. And I want to highlight that because I think all of us are aware from the popular press that the current generation of AI systems is being done on these huge computer farms with huge power requirements. And so anything for a next generation of more efficient computing, and I realize it's not here tomorrow, but that gives us hope for a different way to do this huge kind of compute that's happening for AI and other big applications. Okay, I wanted to go to the areas that are emerging in your lab that are most exciting. I know that one of the areas is that you're looking around at other fields and you're finding some useful technologies that have been developed perhaps for some other field like biology, and it's turning out to be useful in your work. So tell us about that.
Yeah, so my group sort of culturally is a very fundamental material science group, but we also think of applications. So on the very fundamental side, as I mentioned, the $60 million question is how does the molecular structure of the polymer translate into the structure of the film? And the classical material science way of looking at structure is electron microscopy, where you focus a beam of electrons on the material, and that really has transformed material science from an art and an empirical engineering discipline to a science. Now, why can't we do that with polymers? Is because they're beam sensitive. They get destroyed in the beam. But luckily, our biologist friends have been interested in developing techniques to look at matter that's even more delicate than ours with electron microscopy.
Right, and it's still made out of carbon, so at least it's in the ballpark.
Yeah. And so cryo-EM, which was awarded the Nobel Prize a few years ago, has driven a lot of instrumental developments, both the microscope itself, being able to operate at very low temperature, freeze, or it shouldn't be freeze, vitrify water or the electrolyte in the polymer or in the living matter, so it doesn't form ice crystals that would explode cells. And also on the detector side, having detectors that are so sensitive and so fast that you can image with very few electrons per square angstrom, so a very low flux of electrons.
Yes.
So this has been developed, and now we're taking advantage of all these techniques to image our polymers. And so we're able to see not a single strand, but sort of bundles of a few polymers. If they're organized enough, we can see them, where they're going, and we can build these beautiful flow maps of the polymer, making structures playing out, and then from there we try to understand how the charges and the ions move through the structure.
Yeah, so I wanted to ask if you're getting enough resolution, because I know one of the big things about cryo-EM over the last 15 years is their ability to get finer and finer, so that now they're almost able to see individual atoms or pairs of atoms that are, very close together. Are you getting the resolution you need for your kind of theoretical and practical engineering applications?
I mean, that's a very interesting question, because we're not. So the short answer is no. for a number of technical reasons that have to do with essentially how much data we can
Yeah.
collect that allows us to reconstruct it. Uh, so the short answer is no, and the long answer is maybe I don't even care because that might not be the scale. I don't want to know where every single atom is. That's not going to tell me a whole lot. I want to know where these sort of structures at the nanometer to 10 of nanometer, what they look like,
Yes.
because that will tell me where the electrons go.
Yes.
So it's an interesting, different regime of electron microscopy where we don't necessarily care about atomic. It'd probably be great to have atomic resolution, but then how many animals do you need to complete your zoo, right?
Right.
There's going to be so many different things of these that will get lost in the data. On the other hand, what we're interested in is a slightly bigger scale, which is accessible now.
Cool, cool. And then I also wanted to ask about your work in electrochemistry. And so maybe define what electrochemistry is and how all of a sudden these polymers are looking pretty useful in this field.
Yeah, so like I said, we have a fundamental side of the group and an applied side of the group. The applied side of the group is what deals with electrochemistry. Electrochemistry is the branch of chemistry that deals with chemical reactions where electrons are exchanged directly from one entity to another, and there's charges involved and ions and so on.
Does this have anything to do with batteries?
Exactly. So that's the science that
Okay.
underpins batteries, right? So, but there's a lot more to it. You can do catalysis, but let's take batteries as the example of because people can relate to that much more easily. So, like I said, the nice thing with these polymers is that they can swell with electrolyte, and so now you can imagine that all the charges in the electrolyte can get into the polymer easily, and you have a battery that has a high density, and that's also recyclable and so on. And the reason why we're excited about polymers is that an aspect that I didn't mention explicitly is that polymers are completely synthetic materials. They don't exist in nature, which means they're completely engineerable. They're man-made. So if you understand the principles of what makes a good polymer for a battery, you'll be able to engineer the best possible polymer for a battery that does not contain any toxic elements, does not contain any rare, because it's all carbon, hydrogen,
Right.
nitrogen, and so on. And so this is where we like the connection between fundamental and applied. If you understand the fundamental principles, you can then design the perfect polymer that will allow you to make a high density battery that is then kind of ready for the circular economy because the same material, a battery electrode is pretty messy. You have something that conducts ions, a different material that conducts electrons. Then you have a binder to keep them all together because
Right.
those are powders. And then you have the electrolyte. So the polymer can actually do all these things in one material. It can conduct electrons and ions by itself. It's its own binder because it's structurally, it holds its shape. And then the electrolyte will be impregnating this. And so you can see now you don't have to separate all these elements to recycle your battery. When your battery is done, you dissolve the polymer, you purify it, and then you reuse it again.
Oh, this is
So it's
fantastic. So this really is the beginning of a vision for really clean batteries.
exactly that are built for the circular economy from the ground up, not trying to adapt to the circular
And if I'm
economy.
hearing you right, it's also that certain batteries for certain different applications can be engineered separately. So it's not like everybody gets a 9-volt battery. You can say for
Right.
this application, I need higher voltage, and this one lower voltage. And as you said, because of the designability of these polymers, you can make these things specifically purpose built.
Exactly right. Yeah. And then also with different mechanical properties, you can imagine having, I don't know, your electric razor, the battery is actually the casing, right? It's made of plastic.
Right.
Let's make that the battery.
Okay, great. Well, thanks to Alberto Salleo. That was the future of polymers. Thanks for tuning into this episode. With over 250 episodes in our archives, you have instant access to an amazing array of discussions on a variety of topics. If you're enjoying the show, please remember to tell your friends, family, and colleagues about it so that we can grow the audience and grow the podcast. Personal recommendations are one of the best ways to spread the word. You can connect with me on X or Twitter at RB Altman, and you can connect with Stanford Engineering at Stanford ENG.